All right, momentum. Momentum has a lot to do with inertia. So we're going to define inertia again. Inertia is the tendency of an object to resist changes in motion. Meaning, if something is moving, it just wants to keep moving. Something's at rest, wants to stay at rest. It does depend on mass. The more mass something has, the more inertia it has. So then, I think you have heard and used the word momentum. How is this any different than inertia? Inertia can be at rest. If you talk about something like, oh, that has a lot of momentum, it's moving. You would never use the word momentum if something was just sitting there. So we say that this is inertia in motion. It depends on mass and velocity. So of course we have a formula now for momentum. And what can get confusing is the symbol for momentum. I'll give you the formula. It's just mass times velocity. So momentum, I can't use m. That would be mass. So they picked a letter that, I don't know. It's not even in the word. It's lowercase p. Maybe if we were to go back and look at the Greek or Latin word, maybe it started with a P. So I do want to label this. Lowercase p stands for momentum. We know that m is mass, and the v is velocity. Now if we look at units here, in our force unit, we've been measuring every mass in kilograms. Velocity has been meters per second. So when you multiply those together, you're going to end up with kilogram meter per second. And you might think, oh, that's awfully familiar. It kind of looks like a Newton. Kind of. A Newton, I'm going to put this over here, a little thought bubble, was kilogram meter per second squared. Because force had to do with acceleration, so you had the squared. Very similar. Very similar. Force integrated acceleration. Momentum has velocity. There is something called the law of conservation of momentum. And I don't even think we need to write that down. We've done the law of conservation of matter before. What does that mean? When I say law of conservation of, you should always think the first sentence is going to be can't be created or destroyed. Good. Okay, so the law of conservation of momentum would say momentum cannot be created or destroyed. I don't think we need to write that down. All right, we do have two types of problems you could do with momentum, and a lot of them have to do with collisions or things hitting each other. So, kind of make, I don't know, it's like a T-table comparing. There are elastic collisions and inelastic collisions. What does that mean? Let's keep this pretty organized so it makes sense when we go back and study our notes. Okay. So this is going to be the before the collision. I always think about cars. So I'm going to have this little pink car. Headed that way. And a blue truck running straight into it. Leave some room underneath. All right, if it is an elastic collision, an elastic car accident, what that means, they're going to hit each other. And then, in perfect physics world, they're going to kind of bounce off each other, which would be very bizarre to see in real life, as if these are bumper cars. Okay? So that means after the collision, this one is now going that way a little bit. And my truck is going that way a bit. I've never seen a car accident happen like perfect physics world. Typically, even when the cars don't get mangled together, they like crumple and one kind of skids to the side. You don't have anything perfectly like boing. So, how could we use this formula to figure out some stuff here? What you can do is figure out the momentum of this and the momentum of this. So we're going to call this, we're going to be careful here, car 1, car 2. This is going to be after. This is still car 1 and car 2. In physics, we have used before, we're going to call it initial, and after, we're going to call it final. So what could you do here? To figure out the momentum before, you could do mass of car 1 times speed of car 1 initially. Then you would add it to the mass of the truck, which is 2, multiplied by the speed of the truck initially. So how are we going to figure out how they cancel out? You would make one direction positive and one negative. How would we figure out the after? Kind of the same thing. Mass times velocity final plus mass times velocity final. But what the law of conservation of momentum tells us in this situation, this has to equal this. Your before has to equal your after. So if I were to combine those, and that's why I'm trying to draw this and make it very clear. When I combine them, I get M1, oh, this is high enough for everybody to read. M1 times V1 initial plus M2 times V2 initial has to equal the final. M1 V1 final plus M2 V2 final. Now, we're not going to solve these. We're going to save that if you take physics. But I hope you can see that if you're given information, you can solve and figure out what direction that car was going after and how fast it was going. If you're given information, you can figure out missing parts. Before equals after. And that follows the law of conservation of momentum. Again, this situation right here is all elastic. They bounce off of each other. That's why afterwards you have a mass here and a mass there. So then, what if they don't? Hopefully that was enough time for you to finish writing that. I'm going to move the page. Okay. Let's look at a different car accident. We're going to have this car, number 1, headed this way wicked fast. Into a box truck going kind of slow. So how would we quantify that or calculate that? Just like before. The mass of the car times the speed of the car initially, which I told you was very, very fast, plus the mass of the truck, which is going to be a lot heavier. times the speed of the truck initially, which was going kind of slow. So we've got something lighter moving very, very fast, and then something heavy going kind of slow. In that situation, it's hard to predict what's going to happen. Inelastic means not going to bounce off of each other. When these hit, they're going to crumple up and be stuck, attached to each other. Okay, so when I draw my car crumpled up, that's how I'm going to draw that one. Who knows where that tire went there. So these have crumpled and attached to each other. For the sake of this problem, I'm going to tell you that car was going so fast, they end up moving a little bit that way. This truck was going slow. This car was going so fast, it moves the truck. Okay? How do you figure this out? When they stick together, you add up the mass, because now this is just one big clump. So we're going to say, solve this, the mass of the car plus the mass of the truck times the final speed they're going. That's it. Now we've got one clump. We don't have two situations. According to the law of conservation of momentum, before has to equal after. So you could set those equal to each other and actually figure out the final speed and what direction they're traveling in. All right, let's do a practice problem. Example 1. A bowling ball has a mass of 30,000 grams and moves at 2 meters per second. Calculate momentum. Right away, we're told the mass is 30,000 grams and the velocity is 2 meters per second. Solving for momentum, and remember, momentum is lowercase p. Now you should see something. This whole force unit, we've not worked in grams. We've gone to kilograms. So to go from grams to kilograms, you divide by 1,000. That means we're left with 30 kilograms. My formula is momentum equals mass times velocity. 30 kilograms times 2 meters per second. I hear calculators and that makes me sad. 30 times 2 is 60. All right, and our units are kilogram, meter per second. If you need to rearrange the formula and put this into a triangle so that you can write the equation, how you would do that is say momentum is mass times velocity. Just drawing the equation triangle doesn't tell me you know the equation, but it can help you get to the equation. If I say solve for velocity, you would put velocity equals momentum divided by mass. That would be the equation. All right, that's it for our notes.